in this section. In your book, there's a theorem 2.12. It says the following: if A is a n by n matrix and A is upper or lower triangular or diagonal, because if it's diagonal, it's upper and lower triangular at the same time, then the determinant of A is just A11 times A22 up to ANN, or we can also write it with the product symbol. J goes from 1 to n, AJJ. So this is actually what we derived based on the formula. Okay, so as I said, this essentially finishes already all the results you need for your homework for section 2.1. But I guess everyone, if you have never seen determinants before, there's still a strange feeling about, okay, what are we actually doing here? No? Also, we're picking a row or we're picking a column, and then we just calculate this number, and then it turns out it really doesn't matter how we do it. If we do it correctly, we always end up with the right number. Okay, so another way of looking determinants is actually the following, and I just like to do one more example. And yeah.
What does the end result of the equation say?
Product. That's the product sign.
Okay, okay.
Means multiply, no?
Yeah.
J goes from 1 to n, AJJ. Means you just multiply the diagonal. It's the same formula, just with a product sign, no?
Thank you.
Mm-hmm. So just as another example, which I hope clarifies a little bit, it makes us feel better that what we are doing actually, we still don't understand why it makes sense, but suddenly it makes sense. At least no matter what we do, we always get the same number. And that is something which comes out. I can only do an example here. Again, in general, you would do an induction proof. So let's do a general matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Yeah. And we calculate the determinant. So this time I don't give you numbers because it turns out it's important that we don't have numbers. This will actually tell us now a little bit what's actually happening if we calculate a determinant. Okay, and let's do row 1. And as I said, it turns out once you see this, at the end you see, oh, it really didn't matter which one we take. Okay, so if you do row 1, what do I get? So I use this, this, and this, no? And again, this one gets a plus, this gets a minus, that gets a plus.
So you get A11 times determinant
of
A22, A23, A32, A33, minus A12 determinant A21, A23, A31, A33, plus A13 determinant A21, A22, A31, A32.
Okay, so this is just following our rule when we go along row 1. Very good, thank you. And now for these 2 by 2, we use the formula we have, no? So we would have A11, A22, A33 minus A23, A32 minus A12, A21, A33 minus A23, A31 plus A13 times A21 A32 minus A22 A31. Okay, still it doesn't make any sense. It's just a bunch of things. Now I start multiplying. So, and it turns out we have total 2 terms here, 2 terms here, total, we have 6 terms. So we have A11, A22, A33. Then we have minus A11, A23, A32, minus A12, A21, A33, minus minus plus A12, A23, A31. Sorry, 31. Then we have plus A13, A21, A32, minus A13, A22, A31. Okay, maybe everyone can check. I hope I didn't mess this up. 2, 3, 3, 2, 1, 2, 2, 1, 3, 3, 1, 2, 2, 3, 3, 1, 1, 3, 2, 1, 3, 2, 1, 3, 2, 2, 3, 1. Okay, so this is in general the formula for a 3 by 3 determinant. That will work for every 3 by 3 matrix. Okay, but once you see this, and I guess you need to look at it long enough, suddenly you actually see a pattern. So when you look here, we have always, the first index is always 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oh, okay, it's always 1, 2, 3. So what about the second number? 1, 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. Okay, so let's just, for each of these 6 terms, we write the second number. So we have 1, 2, 3. 1, 3, 2. 2, 1. Now I cannot read this. 2, 1, 3. Yeah, here, 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. Okay, so what are these actually? Each one is different. How do we call this? Has anyone seen something like this before? Also sometimes I taught it once, for example, in college algebra, where you do things like this. How do we call this? You have 3 objects, like a red flower, a green flower, and a purple flower. And now the question is, in how many different ways can you arrange 3 flowers? How are these things called in mathematics?
A combination?
A combination would be usually
A permutation?
Yeah, it's actually a permutation. Combination would be without the order, no? So it turns out these are permutations. And it turns out these are all 3 objects you can arrange in 6 different ways. These are all possible permutations. So it turns out a determinant has something to do with permutations. So and why do we get 6? I'm not sure if you ever heard about these things. 6 is because 6 is 3 factorial. 3 times 2 times 1 is 6. That means 3 objects you can arrange in 6 different ways. No? If you have 4 different objects based on this, in how many different ways can you arrange 4 different objects?
4 factorial?
4 factorial. 4 times 3 times 2 times 1. That's also the reason why I don't do 4 by 4, because then we would have 24 terms here. Yeah. Okay, so these are the permutations. So now suddenly you say, oh, okay. So a determinant is just multiplying all numbers in all possible permutations. Okay, so let's start writing down a second formula for the determinant. So it turns out a determinant of A is the sum over all permutations, and I call the permutation sigma. So this means sigma of 1 is 1, sigma of 2 is 2, sigma of 3 is 3. Sigma of 1 is 1, sigma of 2 is 3, sigma of 2 is sigma of 3 is 2. So a permutation is like a function. So this would be the identity function. And then here 1 goes to 1, 2 goes to 3, 3 goes to 2. Here 1 goes to 2, 2 goes to 1, 3 goes to 3. And then we multiply A1 sigma 1, A2 sigma 2, up to AN sigma n. And we multiply these all up and we add them up. Okay. So the only thing which we don't have right in this formula is the pluses and the minuses. So why are some of these permutations with a plus? Why are some of them minus? Okay, so for example, 1, 3, 2 has a minus, where 1, 2, 3 has a plus. So now, this here is also no permutation at all. You can say 1, 2, 3 goes to 1, 2, 3 is the identity permutation. No? You have 3 flowers and you just leave them all in the same space. That's the first one. So now we think about how do we generate permutations? We can generate permutations by just switching always 2 numbers. So 1, 2, 3 is just 1, 2, 3. But how can we make 1, 3, 2? Or we go 1, 2, 3, and now I switch these 2 numbers and I get 1, 3, 2. How can I make 2, 1, 3? 1, 2, 3, and I switch these 2 numbers and I go to 2, 1, 3. How can I make 2, 3, 1? I start with 1, 2, 3. Okay, so this time 1 is not enough. I have to put, for example, I put the 1 in the last place by switching these 2. I get 3, 2, 1. And then I switch these 2. And I get 2, 3, 1. How can I make 3, 1, 2? Oh, okay. So I start with 1, 2, 3. And now, for example, I need to get the 2 in the last place. So I switch these 2. I get 1, 3, 2. And then I switch the first 2 and I get 3, 1, 2. How can I make 3, 2, 1? Oh, that's easy. 1, 2, 3. And I change 1 and 3. I get 3, 2, 1. So for every permutation, I write down the number of, in mathematics, we call them transpositions. You just switch 2 elements. So I just say the number of switches. So 1, 2, 3, I need 0 switches because everything is already there. 1, 3, 2, I need 1 switch. 2, 1, 3, I need 1 switch. 3, 2, 3, 1, I need 1, 2 switches. Here I need 2 switches, and here I need 1 switch. So I can make this permutation, like imagine you have 3 flowers in front of you, and you like to switch them from 1, 2, 3 to 2, 1, 3. And each time you can only change 2 flowers. Then it means to get this, you have to 2 times change 2 flowers, and that's how you reach your permutation. And it turns out this number is called the signum of your permutation. The signum just tells you how many switches do you need. And now you see, if we need 1 switch, we get a minus. If we need 0 or 2 switches, we get a plus. So it turns out -1 to the power of the signum of the permutation. So if you have a signum of 0, this is 1. If you have a signum of 1, it's a -1. If a signum of 2, it's a +1 again. So it turns out every permutation has a certain number of switches you need to make in order to generate this permutation. Imagine you have only 2 hands, so you can always only switch 2 objects. No? And the question is, how often do you need to switch to generate this permutation? And that's what's called the signum of a permutation. So it turns out this is also a definition of a permutation, of the determinant. And this one turns out you can also switch here. Instead of sigma 1, 1, you can also say sigma 1, comma 1. You can actually switch rows. And it turns out that's very easy to see. Then you just use the inverse permutation, which has the same number of switches. So it turns out this formulation makes it very clear. There is no row or column here. This is just one number. It's a complicated number because you always have to find all permutations first, but this is one number. And now the logic is actually different. Once you have this definition, someone figured out, oh, you can actually use the recursive algorithm, which I told you at the beginning, like what our book starts with, and then prove by induction the recursive algorithm, no matter which row or column you start with, you always get this formula at the end. So this is actually historical. It came actually not from how you see in definition 2. Historically, people first know what the determinant is, and then they figured out what is an easy way, also easy to remember, how to calculate this without going into permutations. No? And I think the person who found this other formula, the one in definition 2 of our book, I think that was Laplace, the mathematician Laplace, who found out this formula for a determinant. Okay, again, this is something, it's not in our book, it's not part of our class, but that tells you a little bit, determinants are really, in some sense, also something else. Our book just tells you one cooking recipe, how to get it. No? But what you get is really something like this, without knowing. Okay, yeah. Okay, so.
Oh, I'm sorry.
Yeah.
When you said the number of switches determines the sign, can you explain that part again? Like, how do you know which sign is which from 1, 2, or 0?
No, the 1, 2, or 0 means how many switches do I need to make to reach this permutation?
Yeah, but I understand that, but doesn't it determine the sign?
Yes, because a 2 means -1 to the power of 2 is a +1.
Okay.
-1 to the power of 1 is a -1.
Okay, so that's the exponent. Thank you.
Yes, that's, yeah. Also, the point is, what you might, maybe what you can try to remember is permutations has actually something to do also with, determinants have something to do with permutations, no? So determinants are essentially a clever way, the row or column expansion is a clever way of generating all permutations with the correct sign. Yeah. Okay. And so this finishes chapter 2.1. I hope after the break I can do most of chapter 2.2. And then tomorrow for sure we will also finish section 2.3. And then this already finishes our section on determinants. Also at the end, I will tell you actually another meaning of the determinant, I think at the end of chapter 2.2. And also this also clarifies a little bit why people early on were actually interested in determinants. Okay, so I stopped sharing the screen